Okay. Well, I guess I need to repeat for record. So we're talking about the path length for three-dimensional motion when the trajectory of the particle is given in a parametric form, like in this homework question. That is, you have some explicit functions x of t, y of t, and z of t. You're given some time interval, let's say capital T, and you need to find the path length. So not displacement, but the path length. So, let's say L. So what do you really do? Well, for some random curve, if you zoom in on the curve for some really short amount of time, again, it's in 3D. So this is like changing the radius vector of the particle, which has coordinates delta x, delta y, delta z, that you can write simply as v of t delta t vx, and the same for y and z. Okay, and of course you can talk about infinitesimal things. You would just put dx and dt instead, and then the magnitude of okay, put dr now. The magnitude, the elementary path length during time interval dt, you can find just using Pythagorean theorem, right? Square root of vx squared plus vy squared plus vz squared dt, right? So this is the absolute value of the three-dimensional velocity, right? The three-dimensional speed. And this is dt, okay? And then in order to find the path length, just need to integrate this from, say, 0 to t, or whatever the time limits are, okay? And what are these guys? These are simply time derivatives, right? So put square root of, are you guys familiar with the Newton notation, x dot, y dot, z dot as the time, yeah, just kind of handy. So dot stands for the time derivative. And that integral is actually doable, right? Well, in theory, right? You know how to do some integrals. So as long as, you know, this is not something crazy, you should be fine. So this is the general answer. Again, if you have like zero intuition whatsoever about the given problem, this is the way to compute the path length. Again, don't confuse it with displacement. Displacement is just final position minus initial position vector. Okay, now let's switch to that particular problem. In that particular problem, you actually need to know nothing of this. It's simpler. All you need to recognize is that you can kind of decompose this motion as we discussed, circular motion in the xy plane and uniform motion in the z plane. Importantly, at every moment of time, you can think of the xy velocity and it's perpendicular to the z velocity. Okay, or so I'm trying to say that all you can do is you can kind of consider the two independent paths and do Pythagorean theorem with them. Or you can recognize that in number 5 from homework, wait, which number is it? Yeah, number 4. Number 4 from homework 3, the velocity is simply constant. Just think about it. It's like the vx squared plus vy squared plus vz squared what do you get? You get a squared times omega squared plus 4, the same thing, 4a squared. Are you guys with me here? Yeah, well, just in case we can do Vx as minus a omega sine omega t, Vy as omega cosine omega t, and Vz is just 2a omega, okay? And then you take 3 squares, add them up, and you get that the total velocity is just constant, doesn't depend on time. And if it doesn't depend on time, all you need to do is just multiply it by time to get the path length. Make sense? So that's all. So let's do number 5 now. Number 5. Or 3. So you're given this force. That goes at 45 degrees. So this problem is really just tedious. It is not hard. All you need to do is to just carefully write out the 3 components of the force, get the accelerations, integrate over time twice, and that gives you, but you have to be careful. So maybe it makes sense to actually discuss it, because I don't think anybody got the right answer on this one. Yet this problem is not the hardest. So let's just quickly, right, so, oh, and the axes. Let me introduce the axes. So these are X, Y, and Z. Okay. Then Fx is simply root 2 over 2 times F, right? So Ax is root 2 F over 2M. And let's just call it A for simplicity, so I don't have to write all this combo every time. And then Fy, what is Fy? Fy is this, but it varies over time. So it needs to be multiplied by a trig factor with the uniformly changing angle, right? So we can write root 2 over 2 times F times, let's say, cosine of omega t. And then Z would be the same thing, but with sine. Folks, does this make sense? Why? Well, because in the beginning, Fy is at max and then it decreases. So this is indeed a cosine function. Fz is 0 and then it's increasing, so it's like a sine function or negative sign. It doesn't really make a difference. So then acceleration is obviously a cos omega t, and this is a sine of omega t. Oh, and we're also given that t equals t over 2, where this is the period. That means it's pi over omega. Okay, this is the specific moment of time for which we need to find the displacement or the magnitude of displacement. So let's do it real careful, because I suspect some of you may have just missed some really important thing, technical thing, but still. So what is Vx of t? Yeah, this is a simple question. Expect a quick answer.
That thing times ax times t.
Yeah, so this is just at, right? Good. Now, what about Vy of t?
So you just take the integral of ay with respect to t, and then you get like a times 1 over omega times the sine of omega t.
You guys agree with this? Put the thumb up if you do. Okay. What about Vz?
Do the same thing, but for AZ.
Yes. And what do we get?
We're going to get A over omega, negative A over omega cosine t. Cosine omega t.
Okay. If you folks agree, put the thumb up. If you disagree, clap. I'm talking about the buttons. Well, here is the first tricky point. So when we integrate, right, we should not forget about that constant. And in this case, I guess we lucked out. That constant is 0. But where does it normally come from? How do we fix that constant?
Initial conditions.
Initial conditions, exactly. So let's read the question carefully. What does it say about the initial conditions? What information do we see about the initial conditions?
V0 is equal to 0. So then,
exactly.
Yeah.
So V at t equals 0 equals 0. That's all three components. So these two work automatically, right? Both of these guys are 0, but this is not 0, is it? So how do we fix it? I'm going to put plus a constant, and you tell me what that constant has to be.
A over omega.
A over omega. So you can rewrite this in a more compact form as A over omega times 1 minus cos. Okay. Now let's do displacements. Delta x.
You integrate again, so you get half AT squared.
Mm-hmm. Okay. How about delta y?
So you get A over omega squared times the negative cosine of omega t.
And again, look at this answer carefully.
Plus c plus, yeah.
Yeah. And why do we need to plus c?
Because we know that y naught is equal to 0.
It's actually not given, but you're right. We can just assume it because at the end of the day, we want to find the displacement from the initial position. So that's just natural to assume the initial position was at the origin, right? Does that make sense, folks? So that's why you need to be careful and make sure that delta y at t equals 0 is 0. And the way the integral works, it's not. So you need to put that extra constant. And then the constant has to be what?
A over omega squared again.
Yep. So delta y is actually a over omega squared times 1 minus cos. Okay. Finally, delta z. Need to integrate this guy.
So you get A over omega t minus A over omega squared sine of omega t.
Minus a over squared sine of omega t. Folks, do you agree?
And then
And
constant.
this,
Actually, no, you don't need a constant.
all right. So I can put it, and then you tell me why it needs to be 0. Because these two terms already is 0 at t equals 0. Okay, so I guess that's where you, I mean, if you got to this point, there is no way you get it wrong. It is still tedious because all you need to do now, is to consider delta r squared as, delta x squared plus delta y squared plus delta z squared. And, then take square root of that, of course. But you just need to, generally square this, add them all up, massage a little bit. Oh, and what helps, actually, you probably want to do it before you start squaring things, is this data, right? We know that omega t equals pi. That's what's given, right? So that kills some of these functions. For example, sine of omega t is 0, right? So let me take a different color because now I'm using some additional data. So this is 0. Cosine of pi is -1. Okay. So with that in mind, you just put everything in. Okay. Do you want the answer? There are like at least 2 different ways of writing that same answer. So I'll just put one. But so it's at squared over 8 square root of 1 plus 4 over pi squared plus 16 over pi to the 4th. It's not a nice answer. And that tells me that there is really no nice shortcut, at least to the best of my knowledge. There is no nice shortcut to this problem. Again, there are a couple equivalent ways of getting a single answer. So if what you got looks a little bit different, then maybe it's still equivalent. Just double check. Folks, any questions about this problem? So I know your math is really solid, more solid than your physics. So put your mathematician hat in here, really. So mathematicians never forget the constants. Sometimes in physics, we think we can be sloppy, and that's partially right, but not in this problem. So in this problem, constants are critical. Any questions about it? Okay, let's do the last problem. Again, I don't think, actually one person got the right numerical answer. I wasn't really sure if I followed the solution 100%. I guess I'll need to redraw it. So we're given that theta is 45 degrees, that the masses are equal. The coefficient of friction is 0.1, but we'll just keep it mu. The mass is actually 1 kilogram. We need to find the minimum force with which, actually, let me ask the new person. Are you on the Google Classroom? Do you see the homeworks and notes and everything?
Yeah.
Okay, so you know what we're talking about, right? You've seen this problem before.
I haven't taken a look at the homework because I just joined it.
Okay, but you know where to find them, right?
Yeah.
Okay, good. So yeah, let me draw this force. This is the force that you apply from the right. You push on the wedge from the right, and the idea is to find minimum such a force that will keep the block steady compared to the wedge. Obviously, they move together, but we want this guy not to slide down across the wedge. Okay, so this is what we want to find. And then such that the block doesn't slide down. So I don't think any of you tried. Yes, that's the right answer, Alvin. How did you get it?
All right. That means I solved it right, but I didn't read the question right. So, okay. So basically, what I did was I accounted for the acceleration of the center of mass, sideways, right?
Okay.
So because the block, because there's the only force is downward, there should be no sideways acceleration. So that means since the block accelerates sideways, then the wedge has to accelerate the other direction in order to compensate, right? So then if we can so first of all, the acceleration downwards, it results in like the y acceleration of the center of mass is equal to m over 2m times g sine squared theta when you look at like the vectors.
Okay, I feel that we need to maybe slow down and write something. So I basically, okay, so I wanted to check which approach you take. There are at least two ways to approach this problem. One is just treat it in a laboratory frame. And from what you're saying, it seems it's what you're doing, right?
Yeah.
And okay, what I actually wanted you to do, guys, is start using what we discussed at the last lecture on non-inertial frames, forces of inertia, because I think that's the cleanest solution here, at least to me. So Alvin, you can probably share your solution later then. It helps to know both approaches, but I thought this is one neat way to use what we discussed last time. So anyhow, I want to start exactly as you said, though. I want to find the acceleration, the common acceleration of the two blocks, because of the two objects, if the block is not sliding, they're indeed moving together. They have the same acceleration, and it's sideways, obviously. So A is equal simply F net external. Remember, to be safe, you can put X. Right? Of course, there is force of gravity that you probably may not know how to treat right away, but if you recognize that all you care about is the horizontal direction, then you can just apply that black box trick formula to the x-axis over total mass, which is m1 plus m2. Okay? So this is the acceleration. So F over m1 plus m2, because the applied force is really the only external horizontal force. Does that make sense, folks? There is a whole bunch of forces here. Wait, minus force of friction. Minus force of friction, which we know how to find as well, right? Okay, so and then when you switch, when you switch to the frame of the wedge, things become pretty clean. So let's do the free body diagram for the block in the wedges frame. I'm gonna introduce our favorite tilted coordinates. And here is the block. So let's do the usual forces first. So we have force of gravity pointing down. We have the normal force pointing perpendicular to the surface. It's a frictionless surface, so there is no friction here. But what do we have instead? So what's the feature of this reference frame? It's not inertial, right? So what does that imply?
There exists a fictitious force.
Yep, there is a force of inertia. Which way is it, and what does it equal?
Well, like when you apply the force to it, it's not accelerating anymore, right?
What's not accelerating?
The wedge.
In the wedge's frame, wedge is not accelerating,
Yeah.
but every body in that frame is subject to force of inertia.
I know, but like
That
the wedge is not accelerating in the lab frame either.
it is.
No, but like when you apply the force, right, then that means all the forces are balanced and the wedge is not sliding, right?
Well, if the wedge is not sliding, why would the block not slide? If like in the lab frame, if you are in the lab frame and the wedge is not accelerating, there is no friction to keep the block from sliding on the wedge.
Yeah, okay.
So you understand, folks, first you need to recognize this, and then that tells you the wedge has to be accelerating. So what happens? You push on the wedge, and intuitively you kind of think that it would kind of push the block up. That could compensate for the gravity. Is this idea clear? Okay, but do tell me though, what is this force of inertia? How do we find it? Give me a sec.
Would it be pointing to the left?
Now I should be able to hear you. Say something.
Would it be pointing to the left?
No. Come again?
Hello?
Oh, okay. Now it seems to work. Yeah, so again, you probably told me the answer and I probably missed it. So let's write it down. So force of inertia is always given by the negative mass of the object under consideration, which is m1, times the acceleration of the reference frame. Okay, so the acceleration of the reference frame is to the left. Okay, so that means the force of inertia is to the right, and it's horizontal. Folks, is this making sense? Okay, I think you can now finish this problem, right? You have the free body diagram. You know that the net force must be 0 for the block not to slide, right? So F net must be 0. Just write the two equations down. Let's see, how many unknowns do we have here? We don't know the normal force and we don't know the force of inertia or the F. Okay, that seems to be it, right? There are only two unknowns, and there will be two equations, x prime and y prime equations. And in fact, to be honest, I don't think you actually need to use the tilted frame. It doesn't really help too much. You may want to stick with the standard XY horizontal and vertical frame, because there is like two vertical horizontal forces and one diagonal force. So I would probably just stick with the regular frame. Either frame, it should be all the same. Elvin, you probably found the right way to do it in the laboratory frame. Just judging by your answer. But I want everybody to practice this, because this is a, to me at least, it's a cleaner way to do things. Right? You just add an extra force and you have a single object that you need to consider. Because if you stick with the lab frame, you actually need to consider both objects. You need to do free body diagrams for both objects, write two sets of equations. For me, it's just, more work. Okay. So what do you feel, guys? Do you want to take a few minutes, finish it off, or you'd rather finish it at home? Okay. I'll wait. Actually, you know what? I think it's a good moment to take a break. You totally can use the break to finish it off. Let's come back at like in 10 minutes, 5:43. And if you have nothing to do, I can post another problem. Actually, I can't. I'm sharing the whiteboard. So I'll do it after the break.
Good.
So did you get the answer? Joseph, did you?
Is it 3.5?
Yep.
Hey, that's like the average between mine and Leon's answers. 3 newtons, 4 newtons, just average them.
That means you need to work together with him. Okay. Do you still want to clear anything about it? Do you still have any issues, or you think you're good here? Oh, and Alvin, can you just make sure that Jing Zhang, do I pronounce his name correctly?
I think you should just call him Jing.
Jing, okay. Can you please make sure that he also, so he knows where to view recordings and lecture notes, but can you also have him take the F equals MA 2019?
Oh yeah, sure. I'll tell him.
Okay, thanks. And what's his level in physics?
So he's basically he's taken a physics, like he's taken an algebra-based physics course as well as calculus. So, and then I think like he knows physics C material. So he's basically
Oh,
aware.
he's just taking calculus, so he would not necessarily follow.
No, he's taken calculus.
So he's not like at the like knowing how to do derivatives and integrals yet.
I think he does.
Huh. Okay. And what grade is he?
He is my age, which is 11th grade.
Okay. Good. So like I have a few problems on forces, folks, and we can do them, but I just wanted to like get to the bottom of that swimming pool question. Because it's been a while, so I don't want this to hang anymore. Tell me if you had any luck massaging the integral. No. Okay, well let me show you, and then after that I think you'll be able to finish the problem. So let me remind you, this is where we got to. So this is the final integral. Don't really have space in here, so maybe I'll just copy it. And then we'll just revisit the regular force problems. So we got this, pi equals integral from critical radius to alpha times critical radius. And here we had alpha v dr over r minus omega of r dr square root of v squared minus omega squared r squared. Okay, I hope you still remember what things mean here. Just remind you the main thing. So alpha is the speed ratio, the teacher over the student, which we just called V, okay? And this is a number larger than 1. This is what we want to maximize. So this is just V. Omega is the angular velocity of the student in the swimming pool. R, little r is his radial position. R star is the critical radius. Remember, that's the radius at which his angular speed matches teacher's angular speed. So this is basically what is it? Basically R over alpha. Okay. So the big R is the radius of the swimming pool. So this upper limit is the radius of the swimming pool. So the student swims from the critical radius to the bank of the swimming pool. Okay. Is that, folks, you remember everything? from here now. So the idea was to find alpha max such that there is no good escape strategy. So, and the logic again was that the strategy is described by this unknown function omega of r. It tells like how much tangential velocity the student should have at every radius he's escaping. Okay. The simplest case, like the scenario that we discussed very first, was that omega was just 0. Student would swim straight along the radius, no sideways velocity. Okay, so again, this integral, the way it's written, looks pretty intimidating because alpha is inside and alpha is at the limit. Like, how do we even approach that? And like I said, you need to find some unitless combos, and then integral actually simplifies dramatically. Not maybe so much in terms of the function, but in terms of like conceptually, you at least start seeing what you need to do. So let me just propose these two substitutions for the unitless things. I want to introduce unitless omega that describes the trajectory, and the unitless radius, the variable of integration. So this is what I want to do. If you factor out velocity from under the root, this is what you'd get. So let me just rewrite it like this. The radical can be written as, maybe just this. So I want to rewrite this as 1 v squared times 1 minus omega squared over v squared times r squared. I'll massage this a little bit later. And the numerator, I want to write, actually, you know what? Just call it the numerator. And I'll put it in here. So what I want to do, I want to factor everything out so that I have alpha v over r times 1 minus. So what do I have here then? I have omega of r times r over alpha v dr. Right? I'm factoring dr out, and I want to have a 1 here. I want to call this the unitless omega. Just going to use capital omega. Okay. So what does it mean? That means my omega equals the old omega times r over alpha v. So far, so good. Now, in the denominator, I have this. 1 minus, yeah, I can also do it the other way around. I can write that old omega is new omega alpha v over r. So what I then have in the denominator is this minus v omega squared r squared over v squared, which is v squared times 1 minus omega squared times r squared times alpha squared times v squared over v squared or r squared. Are you guys following? So v and so the r squared and v squared are from here. The rest are from here. Now I want to cancel things. So this is gone. And I want this combo to be my new radius, unitless radius, which is, let's say, x squared. So x equals R alpha over R. Okay. So we're still not done. So let me rewrite the integral for now, just to see where we are. I have pi equal integral from R critical to R. Yeah, because this is just R. Now, what do I have? Actually, yeah, this is squared. So we have alpha V over R times 1 minus omega of R dr. On the bottom, we have V times root of 1 minus omega squared x squared. And this I can rewrite that R equals x R over alpha. You see where it's going now? Cancel the V. Then this times this is exactly x. You see that? So, well, dx, of course, not x, dx. Almost there, folks. Now we need to just replace the limits of integration. So when little r equals R critical, what does it mean for x?
R critical alpha over R, which is just 1.
Yep, just 1. And the upper limit, when R equals big R, what does that mean for x?
Alpha.
Alpha. Okay, now we have all the ingredients to rewrite this integral. You ready? So I'm going to continue on the next slide. So we have pi equal integral from 1 to alpha. Here we have 1 minus omega, we're going to call it omega of x now, over 1 over root minus omega squared x squared dx. Do you agree? Did I miss anything? No? Okay. So this looks much cleaner, doesn't it? Okay, this is the point. You see, I got rid of alpha inside the integral. And that's a big deal, because now alpha is only present in one place, right? So we want alpha to be max, and we already discussed the logic behind this, right? So the idea is this integrand. So again, some of you may be tempted to do Euler-Lagrange equations, but the idea is that there are no derivatives of omega anywhere inside. It's just the omega itself, okay? That means that if you manage to find such an omega that the integrand has its smallest value for that given omega for given x, that will maximize the alpha, because you'll have to integrate for a longer interval, right? Alpha just tells you for how long an interval you need to integrate. Does that make sense? So that's all. So let's just call this some function f of omega, and this is the idea. Minimize f of omega for every x. That will maximize alpha. Oops, what did I write? And that thing I think you can do, right? So what you need to do here is just take the omega derivative and set it to 0. That'll give you an equation for omega and x that you can solve in principle, and that will give you omega as a function of x, and this will be the sought for best strategy, best trajectory. Okay, once you know the best trajectory, you can plug it in the integral and solve for alpha. Like if you look at this equation in the box, there are only two variables really, alpha and omega, ironically, because x is not the variable, right? X is a dummy variable. So everything else is fixed. You see, we started with a lot of different parameters, but at the end of the day, there are only two variables, omega and x. Oh, sorry, omega and alpha. And you find both of them you doing the steps I described. So again, this is now just a standard calculus exercise. You don't really need to know variations. So do you think you can finish? I really want you to finish. I want you to really have that aha moment, because when you see when you'll see what the omega is, you will be actually amazed. So I don't want to spoil that. So do it yourself. Okay, on this happy note, let's switch back to force problems. First, I want to do a couple exercises on the black box track, just to make sure everybody has mastered it solidly. So what did we do? We did Atwood machine the other day. Let's just see how you can get that answer quickly. One, two. So let me put a statement down, and I think we discussed it in detail in the spring, but if that causes any issues, just let me know. We can always discuss it in detail, probably next time. So statement. If the string is massless, that implies that the tension is the same throughout the string. So force of tension is the same throughout the string. Does that ring a bell? Because if the string is like, if it's a massive, say, metal chain, then the tension will be different. It will increase closer, like the higher up you go, it will be greater and greater tension, which makes sense, right? There is more mass hanging from this pivot point, or from this point than from this point. It only makes sense that tension increases. But if the string is massless, the tension is the same throughout the string. And also the tension, the force with which the string acts on either block is the same. Again, if that's a metal chain, that doesn't have to be true. So this is an important statement. If this is not obvious, again, we can discuss it. But from now on, whenever you read problem and you see string is massless, that's what this means. That's what this implies for you folks. Okay. And then using the black box trick, we can find the accelerations, right? That Elvin, I think, wrote last time. A equals F net external over the total mass. And what is F net external? Well, you have to consider all forces really, and then decide which ones are external. But saving that, we can just realize that assuming M2 is larger than M1, that these are just the two forces of gravity, because all the other forces are internal. Wait. Is this sound coming from me? There is, sorry, there is some sound. Can you hear anything? No? Is it just me?
We can't hear anything.
Sorry, I'm not sure what's going on. Here's some sound. Just give me a sec. Yeah, sorry about this. Yeah, so the trick I wanted to show you in addition to this, and again, the spring people may know it, but
Dr. Kagan, so I don't know if you mean like fall, because in spring we only did ENM.
oh, sorry. Didn't we do mechanics at all?
No. So just like to avoid future confusion.
Sorry. Okay. What was I thinking?
I think you meant like fall, last fall.
Yeah, but we only started with you in the spring, didn't we?
I think you were here last fall too. And then you did some mechanics. And like I remember you saying these things.
No, I think we started with mechanics early on in like January or February, but then quickly transitioned. When I came to your school in person, I think we did Newton's laws, right? So probably it's either then or like a following class we did something. Oh, okay, so I'll try to be brief. So what I wanted to say that there is one more force that may cause questions, because if you look at the pulley, so when we say external, we need to say what's in the box, and anything that's out of the box is external. So that needs to be clear. So what do we have in the box? In the box, we would normally put M1, M2, and the string. because the string just connects them. You cannot really not consider it. But it's massless, so it doesn't affect the denominator here. But pulley is not. Pulley is not in the string. So whatever pulley does should be considered external. And assuming that there is no friction, then pulley only does one thing. It exerts a normal force on the string. Does that make sense? Of course, that normal force is distributed. There are a lot of little normal forces perpendicular to the surface everywhere the string is touching the pulley. But you can kind of consider the combined normal force, and I hope it's obvious that the combined force is up. So one thing it does, it cancels the gravity, so the or the tensions on the pulley, so the pulley is not accelerating. But tell me, does it spoil anything for the motion of the masses? Why are we not taking into account? So the claim is that F net external is M2G minus M1G, as Elvin wrote last time. But no mention of the normal force. It's not internal. That's exactly the issue. If it was, it wouldn't bother. So normal force is the force from the pulley on the string, and pulley is not part of the system. So we have to think creatively. And let me just basically tell you this. Normal force is perpendicular to the string, right? And there is no friction. So even though the force is there, it is acting on the string, it is acting on the system, but it is not affecting the sliding motion. Well, if you add the pulley, you will have to start considering the forces acting from the hinge on the pulley. And that you have no control on whatsoever. So you don't want to go that route. So folks, again, some of you may wonder, why don't I include everything in my box? Then there are no external forces. No, if you include too much, you won't have control on like there are always some external forces. Okay, so let's keep pulley away from the box. But the idea is really simple. Normal force does not affect the sliding motion. Okay. And the formal way to put that, and don't laugh, here is the axis I propose to use. Let's call it the U-axis, the bent axis. Again, most of you have not seen it before, so just take a note, the U-axis. Then there is, of course, some other, you can call it the Y-axis or whatever. Then on the Y-axis, you will have like normal force and compensated by something else. But as far as the U-axis is concerned, things become, everything snaps into place, doesn't it? Look at it. This force of gravity goes with the axis. So it enters the net force with a plus. The first force of gravity goes against the axis. So it enters with a minus. Because if you use the standard y-axis, these guys are actually pointing in the same direction. So why would they compete? They do compete if you consider this bent axis. Does that make sense? Say yes, and we'll move on. So, so what I want you to consider, first auxiliary question, and then you'll see that it actually helps in the actual question that I want to ask you. So first auxiliary question, suppose that you have another string here, like, which may be like attached to the hinge of the pulley so you don't mess up with this string. Okay, and you like put a dynamometer here. Okay, what are the readings of that dynamometer? Assuming a massless pulley. Now the pulley is not fixed, okay, or it is fixed by this additional string, and it's massless. So the pulley is massless and suspended from another string. Another string. Find the tension. What do we call it? T nu. Okay. Is the question clear? So the only mass, the only massive things are the M1 and M2, but they're sliding, they're accelerating. So it's not exactly the same as if they were just hanging still. If they were just hanging still, obviously it would say M1 plus M2 times G. But it's not the case when they're sliding. Have you ever seen this problem before? Alan, no? Well, it's an interesting one to figure out, okay? And if you figure this out, there is another question that I want you to consider by Thursday. Triple Atwood machine. So let me try to sketch it. Well, you got the idea, right? So we can call it 1, 2, 3. Given M1, 2, and 3, all masses are given. Assume they're known symbols. Find all relevant accelerations and tensions. A's and T's. Is the question clear? The pulleys are massless. And the strings are massless as well. So if you don't know how to do it like elegantly, just write down Newton's laws and do the math. But I hope you'll find a pattern, and after you find a pattern, you'll be able to handle quadruple Atwood machine, quintuple, and whatnot. Okay. Okay, we still have a few minutes, so let's do some additional problems on like box trick. So I don't think we considered this problem. It shouldn't be hard. And leave some space on the left. So there is a cart that can roll without friction. There is a pulley. The string is supposed to be horizontal and goes around the pulley. And there is another block suspended. This is M1. This is M2. Just to be quick, let me give you M1 and M2 and G, of course. Find the acceleration of both masses. That's a quick question. So as usual, it's F net external. M1 plus M2. So what is that?
It's M1G. And then M1 plus M2.
Okay, folks, if you agree, press a thumb up. If you disagree, clap. Not seeing anything. Abhijit, Joseph, Vincent. Do you agree, disagree, or have questions? Okay, see Vincent, Joseph, Abhijit, what do you think?
I haven't found the acceleration yet.
So, okay, Elvin, maybe quickly just explain it to Abhijit, then I'll ask a follow-up questions actually.
So then the only external force there really is acting on M1, which is gravity. So if you just use black box, then you get M1G over M1 plus M2.
Oh, okay.
Yeah, so technically there is also gravity on M2, but that's canceled by the normal force.
Oh, that's frictionless. Okay.
Yes, yeah, I mentioned that. It rolls. It's a car that rolls without friction. But you're absolutely right. In general, we should not assume that. So I'm going to put another box in here. And of course, connected with a string to the cart horizontally. And this is M3. And there is mu. So how would the answer change?
M1G minus M3 minus mu M3G over M1 plus M2 plus M2.
minus mu m,
M3G,
okay, over,
M1 plus M2 plus M3.
okay, everybody okay with that? So let's call it A1. Okay, let me keep drawing. Say there is, no, it's the left side of the table. There is another pulley. Uh, and there is another mass. M4. How will the answer read now?
No, you can just add M4 to the bottom and subtract M4G on top.
Okay, what do you think, folks? Perhaps I should have asked that question earlier. So let me write what Alvin said and then we'll revisit. Oh. Let's go back to this previous answer. Is there a concern that the A may become negative?
No, because that would just mean it's going in the other direction.
So can that happen?
Yeah, if the force is great enough. Right?
No, I'm talking about A1,
Oh,
the previous example.
Well, this is static friction, right? So then
If this is
so
not
if
here,
it's greater,
pretend it's
then it'll
not
be
here.
0.
Uh-huh. Okay, so this is really, so let me remove this.
You could make like a 2-part answer where it's like if greater than
Yes,
0.
so if M1 is greater than mu M3 and 0 otherwise, right? Because it cannot really accelerate the other direction. Now, what should we say here then?
Oh, so it would change depending on M1 versus M4.
Okay. So
And
when
this,
is this particular answer correct? In what situation?
when M1G is greater than M4G.
Well, we can skip the G's, of course.
Oh yeah.
Is this all though?
I think it also involves static friction, but I don't know how.
Yes, right. So we incorporated. So not only does M1 have to be greater than M4, the
Is mu
difference
M3?
must exceed the friction, right? So you have to write something like this. Does that make sense?
Yeah.
Okay. Now, of course, M1 may be greater than M4, but not by enough, right? The difference may be less than the friction here. Then obviously nothing will be accelerating, right? And you can consider symmetric situation when M4 is greater than M1. In that case, M4 wouldn't have to be just equal or greater, but greater than M1. It would have to exceed M1 by something larger than mu M3. right? You need to overcome the maximum static friction here to have things accelerate. Are you guys following?
Yeah.
Okay, that's almost as hard as it gets with black box track, except for what we haven't really considered yet, and we can't do it now. We need to learn a few more topics before we can do it. But as heads up, we will be able to consider scenarios with massive pulleys. When pulleys are spinning and they're massive, they add to the mix, okay? In a specific way. So once we understand rotational motion, we'll be able to do that. Okay, so this is pretty much all you can have with the black box track. Well, not all. Of course, you can consider some additional problems, and I'll probably throw them in the mix. Say if you have something like this, and you have another block on the incline, right? You can do this as well. But other than that, that's pretty much it. Any questions? No? Okay. So what I want you to do by Wednesday night is basically those two questions in here on this slide, and also finish up the pool question. So this is really neat. Once you get the answer, you'll know you got it right. I mean, if you got the right answer, you will know it's right. Let me put it this way. Okay. Oh, I think it all depends on one important thing. How comfortable are you guys with polar coordinates? Let's say, do you know what the line equation is in polar coordinates? Or like, we already talked about parabola with you, right? We talked about what parabola equation is like in polar coordinates. But I don't think we talked about straight lines.
Like theta is constant.
In Cartesian coordinates, but in polar coordinates, it's so.
Well, yeah,
Vincent, you're thinking in the right direction. So basically, yes, basically you start with saying x is constant or y is constant, depending on whether horizontal or vertical line, okay? And you can convert that to polar coordinates using like x equals r cos theta or y equals r sine theta. Does that make sense? Say, I'm just going to put it in the chat. So you can say that the line equation is r sine theta equals constant, or r cosine theta equals constant. Okay, and usually it's like solve for r. So you say r equals something over sine, or r equals something over cos theta. So that's the line equation. Okay. I just thought you would need to know that if you want to deal with polar coordinates meaningfully. Okay, on this happy note, wish you guys a good week. I'll be looking for your submissions by Wednesday night, and I'll talk to you on Thursday.
Have a good day.
Bye.